Property valuation models often view cities through a flat, two-dimensional lens, plotting past transactions on a simple grid. But modern urban development is vertical. Standard automated valuation models rely heavily on these flat geographic coordinates and past sales data. Because of this, they are hitting a hard accuracy limit. Training algorithms strictly on past transactions makes the model highly brittle. When interest rates jump or rental markets experience sudden volatility, the predictive algorithms break down. This creates a massive blind spot for newly constructed assets. If a building is just finished, it has no transaction history. To a purely historical model, the asset essentially does not exist. This reliance on 2D geographic and historical transaction data creates an incomplete picture, one that lacks the necessary context for dense urban environments. Traditional property valuation rests on three distinct methods: the market approach, the income approach, and the cost approach. The cost approach, specifically the depreciated replacement cost or DRC method, bypasses the new build problem entirely. It evaluates the physical structure itself, calculating exactly what it would cost to construct that exact building today. Yet the DRC method has a strict limitation. It evaluates an asset entirely from an engineering perspective, remaining completely blind to macroeconomic market forces and buyer sentiment. To achieve true valuation accuracy, we have to engineer a pipeline that mathematically fuses these isolated concepts. We must integrate the deterministic 3D physical data of the DRC method with the predictive market adjustments of machine learning. We must pull structural data out of its engineering silo and feed it directly into a real estate economic forecast. This flowchart maps out a 6-stage hybrid architecture. We'll build this system step by step. The first module executes mass land valuation, isolating the intrinsic value of the empty land parcel before any 3D asset is even modeled. This tree diagram outlines the inputs. The system evaluates 37 distinct variables, analyzing physical terrain, geographic location, socioeconomic health, and environmental quality to establish the baseline parcel value. These variables are fed into an ensemble of machine learning models, utilizing algorithms like support vector regression and deep neural networks. The system runs these algorithms through an extensive hyperparameter grid search. It tests thousands of mathematical configurations to accurately capture the highly nonlinear relationships of urban land value. This heavy optimization outputs a mathematically sound 2D base layer. From here, we can begin computationally constructing the 3D asset. With the 2D land valued, the pipeline transitions to the physical 3D asset using the AI and BIM reconstruction cost module. This extracts geometric quantities from a building information model, calculating exact volumes for structural elements. Traditionally, humans translating these descriptions into standardized cost indexes creates a massive bottleneck. This framework solves this using an automated natural language processing cost alignment system. It uses an ensemble of large language models, including Spacy, BERT, Word2Vec, and GLOVE, to evaluate cosine similarity, comparing the text of the 3D element descriptions directly against the standardized cost database. This algorithmic matching instantly aligns the extracted 3D components with current labor and material rates from the construction cost index. By pairing exact BIM geometry with NLP cost mapping, the framework generates a highly precise digital reconstruction cost, eliminating manual human estimation errors entirely. Traditional DRC valuations apply static depreciation timelines. These theoretical schedules rarely reflect the physical reality of an aging, actively maintained building. This architecture outlines dynamic depreciation, creating a continuous feedback loop between a physical asset and its digital twin. Inside a common data environment, extracted COBie data establishes baseline lifespans for every component, integrating with real-world computerized maintenance management systems during operations. As physical repairs are logged by facility managers, the system dynamically recalculates the remaining useful life parameter for each individual structural component. This pipeline replaces broad assumptions with empirical data. The asset's recorded depreciation strictly reflects its actual, maintained physical condition. At this stage, the pipeline has established a rigorous estimate of the asset's intrinsic physical worth, but we must now subject that number to the volatile forces of the open market. This process flow demonstrates how to solve a unique challenge in high-rise properties, calculating the exact value of a single unit relative to the massive whole. The model calculates unit entitlement by analyzing the transaction ratios of different floor plans within the exact same building. The system deploys a gradient-based nonlinear optimization algorithm. It minimizes squared errors across these transaction ratios to find the precise proportional value of a specific unit configuration. Finally, it applies a machine learning-derived suburb-level market coefficient. This injects local real estate hype, rental yields, and auction clearance rates back into the structural DRC value. Applying this optimization and market coefficient grounds the sterile engineering data firmly within the reality of human economics. To test this hybrid pipeline, researchers validated it against a recently completed high-rise residential tower in Melbourne, Australia. The mathematical culmination of the entire framework looks like this. Unit value equals the base land plus reconstruction cost minus dynamic depreciation multiplied by the market coefficient and the unit entitlement. They processed the Melbourne property through this equation, then compared the pipeline's output against the actual recent market transactions for units inside the building. The estimates for one-bedroom and two-bedroom units were 100% within the exact range of actual market transactions. For the three-bedroom units, the pipeline achieved a 0.057% deviation from the actual transacted value. Automated valuation is evolving into a multimodal discipline, one that requires breaking down the silos between 3D engineering standards and probabilistic machine learning to reflect the true value of our